We had some questions on page 278 last night for homework. We're going to do question number 2 here. And we read this. It's a satellite question, right? It's a satellite question that we did yesterday where we have an object orbiting around something else. We know that when we have a satellite, we have a centripetal force. Anytime an object is moving in a circle, there's a centripetal force. But sometimes we need to express what causes the centripetal force, right, Ethan? And in this case, it would be the gravitational force. Sometimes the centripetal force would be equal to the frictional force. Sometimes it would be equal to the magnetic force or the electric force, or sometimes it would be equal to, in this case, the gravitational force. And that's what it is when we've got a satellite. The centripetal force equals the gravitational force. We'd say mv squared over r is equal to g times m1 times m2 over r squared. R's cancel. One of the m's cancel as well. Which m is it that cancels? We've got the mass of the satellite, and then we've got the mass of the central body. Remember what the central body is? The thing that is revolved around here. In this case, the central body would be the planet. Right? So what are we canceling out there? The mass of the satellite or the mass of the planet? It's the mass of the satellite. So we're left with the mass of the planet here. So we got v squared is equal to g times the mass of the producer, or the mass of the planet, over r. What are we looking for here? We're looking for the radius of Miranda's orbit. So we're going to say r goes up by multiplying, and the v squared goes down by dividing. G is, in this case, in every case, big G is the same value. It's 6.67 times 10 to the minus 11. On Earth, on any other planet, on any other object in the universe, G is 6.67 times 10 to the minus 11. So we don't ever need to worry about that. The mass of the producer here, the mass of the planet, is 8.68 times 10 to the 25. And V is the speed, is 6.68 times 10 to the 3. Now, when we solve for R here, remember that we're getting the distance from the center of the planet to the center of the satellite, which in this case is this moon, Miranda. If we were looking for the distance above the surface, then we'd have to subtract the radius of the planet from this. Does that make sense? Right, the number r in the equation is always from center to center. If we have the distance from surface, then we have to add the radius of the planet. If we're looking for the distance to the surface, then we have to subtract the radius of the planet. All right, let's figure this out. I assume we're going to get the answer that's in the book here, 1.30, but let's just do this on a calculator just to make sure. We're going to say 6.67 times 10 to the minus 11 times 8.68 times 10 to the 25 divided by, let's use some brackets here, 6.68 times 10 to the 3, and let's square that, and we end up getting 1.30 times 10 to the 8 meters. All right, so 1.30 times 10 to the 8 meters from the center of the moon to the center of the planet. Again, if we wanted the distance from the surface of the planet, then we'd have to subtract the radius of the planet from that. Does that make sense? Okay, here's another one. Page 279, it says, Landsat is an Earth imaging satellite that takes pictures of Earth's ozone layer and its geological features. It orbits the Earth at a height of 912 kilometers. What are the orbital speed? And what's the period? In other words, the time that it takes to go around the Earth one time. The time for one complete revolution or one complete cycle. All right, it's a satellite, and we know that when we have a satellite, we do the same thing every time. Now, there's a little slight differences between one question and another, but we start off the same way. A satellite says Fc is equal to Fg. The centripetal force is equal to the gravitational force, or in other words, mv squared over r is equal to g m1 m2 over r squared. One of the r's cancels, one of the m's cancel. Which m is it that cancels? The mass of the satellite or the mass of the planet? It would be the satellite that cancels, so we're left with v squared is equal to g times the mass of the planet, or in this case, the Earth, divided by r. Now we're looking for v here, right? So we probably want to say V, yeah, we'd say, let's take this up here so we have some more space. V is equal to the square root of gm over r. G is 6.67 times 10 to the minus 11. The mass is the mass of the Earth, which is 5.97 times 10 to the 24. That's on your data sheet. Divided by R. What value of R do we use? 912? 912,000? Yeah. We don't want to just use that number. We've got to add the radius of the Earth plus this 912. Because remember, that R in the equation is the distance from the center of the Earth. And that's not what we have given to us here. So we're going to say 912,000 meters plus, what is the radius of the Earth? I think it was I want to say 6.38 times 10 to the 6. Is that right? Yeah. Where is it? Oh, it is. It is on the board. Yes, thank you. 6.38 times 10 to the 6 meters. That gives us an R value of, let's see here, 912,000 plus 6.38 times 10 to the 6 gives us 7292,000. So let's put that in there, 7292,000. And we got to square root all that. So, all right, let's go out of here. Let's say 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24. And then let's divide that by the number that we got there. And then, of course, we got to square root that. We should get a speed here of 7389.699. The speed is 7389.699. We're going to round that to 3 digits, but I wanted the unrounded number in case I need that for the next part of the question. 7.39 times 10 to the 3 meters per second. So this satellite is moving at almost 7,400 meters per second, which is pretty fast, right? Sails through space at, I don't know, 30,000 kilometers an hour, roughly. It's about the speed of the space station, by the way, as it orbits around the Earth. About 30,000 kilometers per hour. Hey, we done? No. No, we're not done. We found the speed, but that's not all we're looking for here, right? We want the period as well. What equation relates, well, I was going to lead you too much here. What equation do you think we might use to find the period? JC? Yeah, V is equal to 2 pi r over t. I was going to kind of lead you, and I shouldn't have. I'm glad I stopped. I was going to say, what equation relates the period to the speed? Okay, that's a question you got to ask yourself. Okay, I've got speed. I want period. What equation relates the period to the speed? And it is this one, JC. You're right. So we rearrange that. We solve for t. T is equal to 2 pi r over v. The t goes up by multiplying. The v goes down by dividing. So we get 2 times pi times r. This r is the r that we used over here. It's the distance from the center, again, to the satellite, 7292000, divided by the speed that we just calculated, the unrounded number there, 7389.699. And that equals, I don't know, 2, let's figure it out. 2 times pi times 7292000 divided by 6,200. 6.20 times 10 to the 3. So it takes a couple hours. 2 hours would be 7,200 seconds. It takes a couple of hours for this satellite to go around the Earth one time. It's moving 30,000 kilometers per hour, right? Of course it's not going to take that much time. You get in an airplane that could travel 30,000 kilometers per hour, if there was one that could travel that fast, you'd go around the Earth pretty quick too. Right? Now, is this a different question than what we saw yesterday with our satellite question? Not really. A little bit harder? Yeah, a little bit harder. How come? Well, because A, yesterday we had this number given to us from the center of the planet to where the satellite orbits around. Today, we were given this number. That's not a big deal. We just have to recognize that we want this number, right? We just have to recognize that it's the R value that we want is the distance from the center to the center. And we have to recognize the number that we're given in this case isn't that distance from the center to the center. So don't just blindly, because you're given a value for distance, make it R. Just think about it and see if it's appropriate. And if it's not, then either add the radius of the Earth or subtract the radius of the Earth or whatever you got to do. The second thing that made this a little bit trickier is that you're looking for the orbital period. That's not a big deal. Okay, you solve for that, like literally day one of this unit. You use v is equal to 2 pi r over t to solve for the period, given the speed. So once you get the speed, and the speed isn't that much harder than it was yesterday, you just had to worry about the r value. Once you get the speed, this becomes a day one of circular motion and gravitation question. V is equal to 2 pi r over t. Now, I know sometimes it seems a little bit trickier than I make it out to be, but in the end, that's what you got to boil it down to. Okay, just make it. Like if I'm saying like, look, this isn't that hard, and this is why, and you're following along with that, then make it easy like that yourself. Right? When you're working on this for homework or in class, like you're going to for the next few minutes, turn it into easy questions. Just hammer it down to what's really important here. All right, we got 2 questions that I want you to work on, page 279, and that will be the end of the unit for you.